Following the videos from K-Maps, we're now going to go into a new topic, and this is the logic IC topic. So what we want to do is consider a bunch of logic gates in a black box. Now we don't know the connection of them, we just kind of know that we have a bunch of logic gates grouped together. Now that theoretical black box is going to be an integrated circuit or an IC. Now the first kind of IC we want to look at is a binary decoder. So the binary decoder converts binary code to a set of outputs, and for the number of outputs, it's going to be equal to 2 raised to the number of inputs. So maybe more simply stated, the binary decoder sets the position of the output based on what value the input is. Now the first example we're going to look at is this 2x4 decoder. So with the 2x4 means we have 2 inputs and 2 raised to the 2 is equal to 4. So we have 4 outputs given by Q sub 0 all the way to Q3. Now sometimes you may have an enable pin, and the enable pin works in the following way. When the enable pin is high, the device is active, and when the enable pin is low, the device is inactive, or every output is off or equal to 0. So if we look at all the combinations that we can have, we have the enable pin 0 and 1, and then we have all of our X, Y inputs. So with the enable pin, we get 8 possible outputs, but if we don't have an enable pin and it's always active, we simply get 4 outputs that are possible. So we can divide this table for when we have the enable pin inactive and active. So when the enable pin is inactive, no matter the combination of X and Y, the outputs are all going to be 0. Now when the device is active, when the input for X and Y is equal to 0, 0, which would be a decimal 0 value, that's going to trigger the pin Q0. And the rest of the outputs are going to be low. Now when the inputs are equal to 0, 1, or a binary 1, only the first term is going to be high, and it's going to carry through for the number of combinations that we can have. So you see this diagonalization of the table when the enable pin is high. So returning to the age-old question, what's the point of all this? And to examine that, let's consider a function given by the sum of products for the term 0 and the term 3. Now we have 2 options we can think about. We have option 1, where we take this function here and strictly implement it in a logic circuit as we've learned. And the second option is to use a decoder, because when we would have X bar, Y bar, it would trigger this output here, which would trigger this OR gate for F to equal 1. And when we would have X, Y equal to 1, 1, it would trigger this last output. And again, we would get F equal to 1. So which is better? Well, recall that this is some black box with a bunch of logic gates in it. So we have a bunch of logic gates, and then we have an OR gate. Now here, we have an OR gate, and we have 2 AND gates and 2 inverters. So that's not really that many gates. So from a number of components and complexity side of things, option 1 might be better. But I want you to consider the flexibility of using the decoder. So let's say we had F equal to that original function, but now we need to change it. And we need to change it on the fly, such that F is equal to the first term, second term, and third term. Now we can express this as X bar Y, X Y bar, plus XY. And this function is not equal to option 1. We would have to redesign the circuit. And that's not too much to complain about, but let's consider using the decoder. So we know that M1 would correspond to Q1, M2 would correspond to Q2, M3 would correspond to Q3. So what we can do is take our decoder circuit and simply connect these lines like this, and we've disconnected Q0. So on the fly, we were able to change option 2 without even having to think about how to redesign option 1. And from this, we can say that option 2 is more flexible to changes, and maybe that's needed. So let's look at another decoder, and it is going to be the 3x8 decoder. Now for this example, we're going to try to make a 3x8 decoder with 2x4 decoders. So if we have a 3x8 decoder without an enable pin, we simply have 3 inputs and we have 2 to the third outputs, or 8 of them. So we have 8 combinations because that enable pin is always high. We're not considering when the enable pin is low. And again, you can see we get the diagonalization in the truth table. So it's pretty much just an extended 2x4 decoder. So let's look at how we can do this. So on the right here, again, we have our truth table that we want to try to match. And we have 3 inputs, W, X, and Y. Now the question is, what do we do with a 2x4 decoder? Well, because we have more than 2 inputs, we're probably going to need another one. But how do we tie them together? So the first thing that we can do is arbitrarily set one of these decoders equal to these values Q4, 5, 6, and 7 here, because they're just pin numbers. So we can do that just by setting the second decoder with 4, 5, 6, and 7 for the output. And if we threw a black box around both of these decoders and simply just had the pins coming off, you wouldn't know necessarily that you had 2 2x4 decoders here. And if you look at X and Y and split the table down the middle horizontally, you can see that you have 0, 0, 0, 1, 1, 0, 1, 1, and then it repeats itself. So maybe X and Y are the best inputs to use. So now that we guessed on our inputs, let's just complete these decoders by having an enable pin. We don't know if we need it yet, and if we don't, we can always just call it always high. So now we can start to look at these combinations. Now we know if we have X equals 0 and Y equals 0, we would trigger both of these events, which would trigger Q0 and Q4. But we only want Q0 to be high. We don't want to consider this term. So how can we do that with our last remaining input, W? Well, we know if we turn the enable pin off, this second device here won't even be on, so Q4 would also be a 0. So we can take W and tie it to this decoder, because if W was equal to 0 right here, this entire device would be off. But we want this one to be on, so what we can do is tie an inverter onto W and tie that to the enable pin. So let's look at what happens now. If W equals 0, we have 0 at this enable, which means this device is off. After the inverter, W equals 1, so this device is on. Now X is equal to 0, and Y is equal to 0, which is the same down here for the second decoder. So looking at the second decoder, X being equal to 0 and Y being equal to 0 would trigger Q4, but remember the enable pin is off, so nothing happens to any of the inputs. They're all equal to 0. But up here, we have Q0 being triggered and the enable is high, so this line goes high while all of these remain 0. So then for this first term, where we would have 0, 0, 0, this is what all of our outputs would look like. And if we look going horizontally, we have a 1 here for Q0, so that matches, and everything else is equal to 0, so that matches.